lesson 5.1. Basically, it's going to be the derivative of the exponential function of y is equal to e to the x. We can see by the little graph provided on the left that what the function of y is equal to e to the x is going to look like. And we've mentioned logs in the past, and we're going to be mentioning logs or lns a lot in the upcoming lessons. So you can actually see that they are flipped along the y is equal to x axis. If we look at the table, we can actually see the properties of y is equal to e to the x. That's what we'll be focusing on today. So we can see that domain is an element of all real numbers, that the range is going to be anything greater than y is equal to 0. That means there's going to be an asymptote at y is equal to 0, horizontal asymptote. And just like an exponential function, a basic exponential function has a y-intercept of 0 and 1. The last one is, we'll talk about again later on in lessons, but if you take the inverse functions, they actually cancel each other out. So I think that's self-explanatory. The next concept we're going to talk about, and we're not going to really dive into it too much in this course, is Euler's number. So we can see that we have this letter E that we keep on referring to. It's actually called Euler's number. And there's a couple of formulas and some proofs that actually explain how it's derived and everything else. I'm not going to divulge into it because it's not important for our course. And again, you can read at your leisure. Another thing that we're going to mention, and it's not part of our course for this year, it will probably be part of your course in Calculus 101 in university, is the hyperbolic functions. Okay, the rules for hyperbolic functions are different than that of the trig functions, which we'll be talking about in a few days. So just to get some complete notes, let's take care of this here. And again, we're going to talk about Euler's numbers and all its derivations, but I don't think I'm going to be asking that in any kind of evaluation. So here we go. So it says estimate the number E using the formula 1 above, and by taking n equals a larger number, in this case here they're saying 100,000. So in essence what we have is when I have E, which is equal to the limit as n approaches, in this case here they want us to use 100,000, and it's going to be of 1 plus 1 over n to the exponent n. I think I should make this just basically infinity. So a big number. And then for the evaluation, I guess we should actually change it over to the limit as n approaches 100,000. And now just trying to show it as a complete set of notes. And when we actually take the limit, we're actually going to say that E is equal to 1 plus 1 over 100,000. It's the exponent of 100,000. Now you need your calculator for this, and it's going to give you a non-terminating decimal and a rational number, and it's going to be equal to approximately 2.72. For the second example, it's an estimate using formula 2 above, which is on the previous page, so I'll write it down for you. So really what we have to understand is the root of E is really E to the 1/2. And that's going to be equal to approximately the formula. When I change it over, it's going to be 1 plus 1/2 over 100,000, the exponent of 100,000. And if we put this in our calculator, we get approximately 1.6487 or 1.65. So I was mentioned before, we don't have to really worry about those formulas per se, because we're basically doing derivatives and equations and all the other kind of good stuff. So let's see what happens when we actually take the derivative of e to the x function. So the first thing we have to do is remember we're going to use the chain rule, or the product rule in this case, right, where it says that we're going to take the derivative of x squared times e to the x plus x squared, which we don't need brackets around, times e to the x derivative. So when I do this, what we're going to get is derivative of x squared is going to be 2 to the x times e to the x plus x squared times e to the x. So the derivative of e to the x is e to the x times the derivative of the exponent, which is going to be 1. When I simplify all this, I can actually factor out an x and an e to the x. So I can factor out x, e to the x, and what we're going to be left with is 2 plus x, or to write out a little bit better, we'll always put the variable first. For the second example, I'm going to rewrite it slightly different. I know that this is really the same thing as saying e to the exponent 1 over 2 times x, or it's equal to the root of e to the x. So we get a good visual of what's going on, all right? Or another way we can actually write this is by saying we have e to the x all to the exponent 1/2. So when we're doing the calculation, we can actually see which one's going to be the best one. I think the last one's going to be the best one for us. So if I'm taking the derivative, basically I take the derivative of the whole entire function. So it's going to be drop to 1/2. We have our e to the x to negative 1/2 times the derivative of the inside function, which is e to the x, times the 1. I'm going to clean this all up. So if we clean this all up, we have our 2 root e to the x on the denominator. We have our e to the x on the numerator. So when I rationalize this and clean up even some more, my final answer should look like e to the x under a root sign over 2. You may need a couple of seconds to process that. Going on to the last one, that's going to be equal to, well, derivative of e to the x is really e to the x itself, so it's going to be e negative x times the derivative of the exponent, which is going to be negative 1, or we're going to have negative e to the exponent negative x. Let's do example 4. So again, it says differentiate. So we know that the derivative of e to any kind of exponent is going to be itself. So there's my e to negative 3x times, we have to take the derivative of the exponent. So it's going to be negative 3. And when I simplify it, we're going to have negative 3 e to the negative 3x. The next two are more indicative of test type questions. So let's see how we do this one. I'm going to rewrite it slightly different so we can actually get a good visual. So in this case here, it's really the same thing as saying e to the exponent of negative 1 x to negative 2. So if I take its derivative now, what we're going to have is something like this. We're going to have the derivative of the e function, which is going to be itself, times the derivative of the exponent. So it's going to be drop to negative 2 times negative 1, which is going to be 2. And we know it's going to be x to the exponent negative 3 reduced by 1, so that goes on the bottom, x to the exponent 3. And we can technically bring down the e to negative 1 over x squared as well, but I'll just leave it alone. For the last example, same thing. I'm going to just change it to something easier for us to view. So it's going to be x squared plus 1. So when I take its derivative, I have the same function again, times derivative of the exponent, which is going to be 2x. And of course I made a mistake, so let's go back and fix that up. So I forgot to put the 1/2 there. So let's try this again. So when we take its derivative, we're going to have derivative of the function. So it's going to be e to the root of x squared plus 1, the original function, times we take the derivative of the exponent. So it's going to be 1/2 x squared plus 1 to negative 1/2, times we got to also include the derivative of what's inside the bracket. So times the 2x. So we can actually simplify by crossing out the 2 there. So now the way this would look would be on the numerator, we still have our e to the root of x squared plus 1. And we also have on the denominator, we have that x squared plus 1 to the exponent negative 1. I'm going to put that in the bottom. So we have x squared plus 1. And we have an x that's all by itself that goes in front. And there we have it. And that's all for today's lesson.